know how to compute occlusion that you can do with scenes where object A is blocking object B and things like that. So that's good. Remember what I said about rotation, about how CNNs are very bad at rotation and create blurriness and things like that. This is the result of RenderNet. So I can rotate it 360 degrees and I can still generate really, really good images out. So that is the reason why you should not force a CNN to do rotation. It's a waste of resource, basically. Yeah, just to compare again, this is what the CNN produced when you ask it to rotate the chairs, right? It's very blurry, and this is what you have when you ask RenderNet to rotate the chair. So that's good. It can also do, RenderNet can also deal with texture. So here you have face models with like skin texture and colors and things like that. So in addition to rendering, it also needs to learn how to do texture mapping. So given a texture, a 2D texture, how can you map a point 2D to a point 3D? So this is a input geometry, voxel. This is the result of, so the texture in this data set is compact, is compressed down into a vector. So the texture is represented by a 99-dimension vector, and this is the ground truth. So this is the result from RenderNet, and that's the ground truth. So that's pretty good for something that was trained on mean square error.
So the input like also the line position and the camera pose, right?
Yeah. And
what about texture?
So the texture, well. Yeah. So the texture is a 199-dimension vector.
Okay. So basically, the model can learn a kind of texture mapping.
Yeah.
Normally, texture mapping is kind of done manually by artists, by modeler, right?
Yeah.
And now the RenderNet can learn from it.
Yeah.
That's great.
Well, yeah. Yes.
Because in my team, there's just one guy who texture mapping manually, and it's kind of very complex or something. Hopefully,
yeah.
use it. And,
yeah.
I'm not sure about how
right now, it will
generalize.
So right now for face, it does pretty well, but for more complex objects, it's two things, because one thing is more complex, but also we don't have as many training data.
Okay.
Right, because texture is very expensive, right?
Exactly.
So to have texture model to train this thing is also expensive.
Yeah.
So it's like two problems actually. It's something I'm trying to solve in my current project as well.
Yeah.
But, we can talk about it over lunch.
Yeah, sure.
So once we have this, we can do things like keeping the same geometry but changing the texture, so that's good. Same texture but different face, so that's good. You want to see how your face looks like when you're fat or when you thin or whatever. You can change the lighting condition, so that's good. So that's texture. So now, I really want to convince you to not use CNN to do rotation. So I compare our RenderNet with state-of-the-art in terms of generating chairs, because that's the data set. So this is one of the first work that used convolution neural network to generate and rotating objects. So it was also trained on the same chair data set with RenderNet, so that's good. So the first A, this corner, what we're trying to show is that if you ask this network to do rotation, the first two rows, you see that it's very blurry, but RenderNet has no problem, so that's good. For this one, what we did is we tried to change the lighting. So this model again takes in the object, a view, and the lighting. So when we want to change the lighting, it's very, very confused and very blurry. Again, for RenderNet, it's still working well. And finally, again, comes back to generalization. Because this network was trained on the chair dataset, when we're trying to ask the network to render other objects, it fails perfectly. But for RenderNet, because it can generalize really well, it does it with snap a figure. So that is rendering. Now we're going to show how you can use RenderNet, which is differentiable, to do inverse rendering. So again, you can frame inverse rendering as an optimization problem. So given an image I that you want to recover the geometry Z prime, pose theta, lighting, and texture, you want to get these inputs given given F, which is a trained RenderNet. We want to get the input so that the image generated by RenderNet is as closely related to I as possible. So that's a minimization problem. So the first column is the input image. So that's the face image that we want to recover, the 3D models, and the lighting, the texture. So that's what we want to recover. The second column is what is produced. The second column is the best results produced by RenderNet. What I meant by that is that so this is the best result we have in terms of like using the geometry and the lighting and the texture that we recover. So this, just to show how closely we can reconstruct the image. And now because we have the geometry, so this is the geometry that we recover from this image, it's very easy to basically manipulate the image. So now given the same face, we can change the rotation of the face. We can change the lighting of the same face, and we can also change the texture of the same face, because now we can recover the input. So that's the interest of computer vision. Given the image, we try to recover the input so that we can manipulate it and learn from it as well. Again, we compare with another state-of-the-art who tries to solve the same problem, but they recover all of the inputs in the latent space. So that's one thing. And they also does the 3D rotation in latent space. Okay, so they does all of them in this Z vector. So what they did is that they learned an autoencoder where they learn a representation and they try to decompose this learned representation in the sense that if it's a 200-dimensional vector, the first 10 will control the geometry, the next 10 will control the lighting and things like that. And by manipulating each part of this vector independently, they can manipulate different parts of the image. So that's the idea of this paper. The difference that, again, they did is all of this in latent space. They never recovered the full geometry, and they did the rotation in the latent space. So this is RenderNet, and this is their work. I think they call it Deep Convolution Inverse Graphics Network. So for some reason they couldn't do with color. I don't know why. This is from their papers. I just took it from their paper. So they try to solve the same task. Given an image or a series of image on the first column, they try to get the input so that they can recreate the image as faithfully as possible. So this is the best result. It's already much more blurry than RenderNet. But the interesting part is that when they try to rotate the face, it's become very, very blurry because they did it in the latent space. Like, if you think about it, the latent, like, how can you do 3D representation in this? Like, there's no regularizer in this space that help with 3D rotation. So this is the